Hello folks, and welcome to this tutorial on scalars and vector. In this tutorial we're going to take a look at distance and displacement, speed and velocity, other types of scalars and vectors, combining vectors, and resolving the components of a vector. Before we go through all this, we need to understand what scalars and vectors are. A scalar is a quantity that has a magnitude or size to it, but has no direction. A vector is a quantity that has both magnitude and direction, and we'll see both of these played out when we take a look at distance and displacement. Let's consider someone going on a journey. The red line represents the distance the person has travelled. If we measure the length of the red line, we can see that the person will have travelled approximately 8 meters in distance. The blue line represents the displacement. This is the shortest distance between 2 points from start to finish. To avoid confusion, the letter for distance is given as the letter S. And if we measured this distance, we could do a calculation or we can measure it using a ruler, we'd probably get something approximately 4.2 meters in length. When you look at the red line, you can tell that there's no particular direction. In fact, there are multiple directions for the distance that was travelled. Therefore, distance must be a scalar quantity. It has no particular direction, a size only. With displacement, when you're looking at the blue line, you can tell that it's one straight line from start to finish, and that you can have a particular direction with. Often, the direction is expressed as an angle. This could be from the vertical line to the resultant line for displacement, or as a bearing where you have a north line drawn towards the top of the page and you're going clockwise with your angle to where the resultant line meets for your displacement. Really, the direction that you're stating depends on the question that's being asked, but for now we will say that our displacement is 4.2 with a bearing of 135 degrees. And please note, whenever you're quoting a bearing has to have 3 figures. So say our bearing was actually only as far as here, then it would be something like 0.35 degrees or something like that as well too. But that's just me making up some figures. And just to recap here, distance is a measure of how far a body has travelled during its journey, and displacement is the shortest distance between the start and finish. Now let's take a look at speed and velocity. Speed deals with the rate of change of distance and therefore is a scalar quantity. Velocity deals with the rate of change of displacement and is therefore a vector quantity. Note, to avoid confusion, I've used the word speed instead of using the letter S, and I've used S where I would normally keep distance for my speed distance time calculation in my velocity equals displacement divided by time calculation. We now have 2 new calculations. Let's imagine that the time it took to make the journey was 2 seconds. Our speed calculation would therefore look like this. So here I'm using the distance of 8 and the time of 2, getting a speed of 4 meters per second. If we do the calculation for velocity, however, we get a different answer. This time we're substituting in the displacement of 4.2, dividing it by the same time, 2 seconds, and getting 2.1 meters per second. Because displacement is the shortest distance between 2 points, your velocity will always be a lot smaller than your speed. And because this is still a vector quantity for velocity, we also still need to quote the bearing. And again, just to recap, speed is the rate of change of distance. It is a scalar. And velocity is the rate of change of displacement. It is a vector. Here are some other popular scalars and vectors. Distance, speed, time, mass, and energy are all quantities that have magnitude only. They have no direction and therefore are scalars. Displacement, velocity, acceleration, and force all have magnitude and direction and are therefore vectors. Whenever you have 2 or more vectors acting, you'll often have to combine them. We'll begin with starting off with looking at collinear vectors, which are vectors which act within the same plane. Consider a body where you have 2 forces acting in the same direction, 2 newtons and 3 newtons. A general rule would be to take the two vectors and add them together nose to tail. If you do this, you end up with a resultant. In this case, we're dealing with forces, so we'll have 2 newtons plus 3 newtons, giving us a grand total resultant force of 5 newtons. If we look at a scenario where the two forces acting on a body are opposing each other, we need to take them away, and the nose-to-tail diagram would look something like this. We would be going 3 newtons in one direction, then 2 newtons in the opposite direction, which would leave a resultant of 1 newton, and that would be going to the direction in the right. If we look at a scenario which involves 3 vectors, you can see there's 2 newtons acting to the left and 3 newtons acting to the right. If we combine the two, it should look something like this. So you can see where we started from, where we're ending up. We actually have a difference of 1 newton, and that 1 newton difference is acting in the opposite direction, so we have 1 newton acting to the left. Let us now consider vectors acting perpendicular to each other. To determine the resultant, we need to follow the rule as before, drawing the vectors nose to tail. Once drawn nose to tail, we can now add in our resultant force. Now that we've drawn it nose to tail, you can actually determine what the direction is of the resultant. To determine the size of the resultant force, you can do a scale drawing and you can measure the side using a ruler. If we do so with this, we would get something along the lines of 5 newtons. As we know, this is a 3, 4, 5 triangle, so it was going to be 5 newtons anyway. But you could have more complex numbers, and you may have to use some trigonometry to work out what the side would actually be. Let's take a look at the vectors this way. So resultant is labelled capital R. The vector along the x-axis is x, and the one along the y-axis is y. If we take a look at these and use this formula, we should be able to work out our resultant. It can be rearranged this way, and then if we plug our numbers in, we should get our answer of 5, like so. Now, because this is a vector quantity, we do need to know the direction that it's acting in. And what we'll do is we'll work out the direction with respect to the x-axis. So we're going to work out an angle, theta, here. And to work out this angle, we're going to use SOHCAHTOA. I've relabeled the sides of the triangle so that we have 3 newtons as our adjacent because it's right next to the angle, 4 newtons as our opposite because it's opposite to the angle, and 5 newtons as our hypotenuse. Now I have all 3 quantities for the sides of my triangle, which means I could actually use any one of the rules for sine, cosine, and tan. So I could do opposite divided by hypotenuse, adjacent divided by hypotenuse, or opposite divided by adjacent, and then do the inverse of either sine, cosine, or tan. I think I'm going to pick tan today though, so we'll do tan theta, which equals opposite divided by adjacent. So tan theta will equal 4 divided by 3, and then if we do the inverse tan, we should get an answer of 53 degrees. So our final answer is 5 newtons at 53 degrees to the x-axis. Finally, let's take a look at resolving a vector into its x and y components, its perpendicular components. And this is a skill which is very important in higher. One example could be in projectile motion questions. And we'll take a look at this from a projectile motion point of view. What I'll do is I'll say the vector has a velocity of 20 meters per second. And I'll say that it is 30 degrees to the x-axis. I'll draw the y-axis in here as well. So, This is my x-axis, this is my y-axis, this is my resultant. I know that the resultant is technically my hypotenuse. My y-axis is my opposite, and my x-axis is my adjacent. So if I use a little bit of my knowledge in triangles, I should be able to work out what the size of the velocities would be in the x and y planes. So let's start off with the y-axis. We know y is an opposite, and I have the hypotenuse, and I have the angle, so I should be able to use the sine rule for this one. So sine theta equals my opposite divided by the hypotenuse. And if I substitute the values in here, sine of 30 is going to equal my opposite, which is my y-axis, so I'll put in y just to avoid confusion of O's and zeros, and then divide that by the hypotenuse, which is 20 meters per second. I can rearrange this now so that my y-axis equals 20 multiplied by sine 30, like so. And if I do that, I get an answer of 10 meters per second. If we're resolving the x component, again, we know the hypotenuse and we know the angle. So for this one, if we're using x as the adjacent, we should be able to use the cosine rule to work this one out. So if I use cosine theta equals adjacent divided by hypotenuse, and then substitute what I know, so cosine 30 equals my adjacent, which is basically the x component, divided by the hypotenuse, which is 20, I can then rearrange this so that x equals 20 times cosine of 30, and then x should come out as 17.3 meters per second. That is your components resolved. 17.3 meters per second for the x-axis and 10 meters per second for the y-axis. So just to summarize a few points, guys. First one, always join vectors nose to tail. Vectors going in the same direction are added together. Vectors acting in the opposite direction are subtracted away from each other. When combining perpendicular forces in the x-axis and y-axis, the resultant equals the square root of x squared plus y squared. And to find the angle or resolve perpendicular components, we use SOHCAHTOA, where sine theta equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent.